So imagine you have $1,000 to spend in stocks, and you have these three options. And now the smart thing to do is look at the financials. So let's open up all the financials. Okay, so you have to read these numbers, but not what do these numbers mean? What do all these numbers mean? So you start panicking. You walk around the room trying to find a solution. Maybe you jump up and down trying to get yourself exercised and try and find a solution maybe. Or you run around screaming panic and devolve into disaster. And now you will probably keep staring at the screen for a bit. Maybe you should take a break first. Newcomb-Benford's Law by me. Okay, it's also called Benford's Law or the Law of Anomalous Numbers. So the history, the math, the applications. And first is the history. Well, so the first recorded person to find it is Simon Newcomb, an astronomer and mathematician that was kind of influential more in astronomy. But in 1881, he noticed, like, in a book of logarithms with just answers to like all the logs, and it was organized by first digit. So he noticed the earlier pages were dirtier than the last pages. So he wrote a paper and wrote a formula: log n plus 1 minus log of n. Oh yeah. But then his idea was rejected by mathematicians, partially because no one really cared. And here is the 2-page thesis he wrote on this. This is Frank Benford, who is now credited with Benford's Law only because he plugged it into real-life data sets such as the area of rivers, population, drainage, atomic weight, addresses, and these averages of these 20 sets came very, very close to Benford's Law. And I have chosen to use Newcomb-Benford's Law this round. And other notable people have Mark Negrini and Walter Mabane, using it for financial irregularities and voter fraud, respectively. And now it's time for the math. I'll let this finish. So the graph of digits, and these are all the frequencies of all the digits from 1 through 9, because this is only looking at the first digit, and you could plug it in for the first digit. You could have this equation that you could quickly make, but the actual equation is a logarithm, log 1 plus 1 over d. Here's another way to look at this, and the place I found this is called the stripy hat. And you can read this part. This is the probability density function for log of x, and this is where the leading digit will be 1. And according to another math law, all the black area will be covered 30.1% of the area in that. So, good question. Why is the probability of each number not 1 over 9, instead 30.1% and random numbers? Here's the proof. So these are the 9 numbers. Let's say you were to double the numbers. 1, and the leading digit was shown right here. And then 5, 6, 7, 8, 9 double to 1. Meanwhile, the rest each only get 1. Now, to better fit with Newcomb-Benford's Law, a larger size or a larger magnitude and a smaller chi-squared test result, these are the steps. It's just simply to find the difference between the expected and observed frequencies, which is very helpful in Newcomb-Benford's Law. Now, beyond the first digit, Simon Newcomb theorized beyond the first digit here, and here is the formula for this now, where n represents which digit and d represents the number from 0 to 9, and k just represents the term. Now, explaining Newcomb-Benford's Law, You would think it's easy because it's everywhere. There has to be enough proof that there should be an explanation, but there isn't. So there's 4 competing theories on this. We have multiple probability distributions, multiplicative fluctuations, scale invariance, entropy related stuff. I don't know if it's really competing. Multiple probability distributions. It's where uniform distribution does not even work with Benford's law. So in a set like that, such a set would be like a set which is all numbers from 0 to 100. That's uniform distribution. And that would fail Newcomb-Benford's law, but when combined with another uniform set, slowly and slowly it starts to reappear again. And then there's multiplicative fluctuations, and this goes back to that proof I showed you with why it was 1/9, the probability, because multiplicative fluctuations also follows Newcomb-Benford's law, which is why the stock market should also follow Newcomb-Benford's law. Additive fluctuations do not. Scale invariance. So scale invariance involves scale invariant data sets, and it's where sets independent of the units that the data is expressed in. So it doesn't matter if it's in feet or meters. And then base invariance, and that implies base invariance, which is when changing base still gives the same leading digit. This is directly related to Newcomb-Benford's law. However, there's no accepted definition. This used to be the predominant definition, but fell out of favor. But a few interesting things. So Newcomb-Benford's law works with all bases, and it works with the Fibonacci sequence. I believe it works for pi sequence, maybe. Lists and stuff with low orders of magnitude like height, weight, IQ scores, they do not follow Newcomb-Benford's law. And now we're finally getting into the applications, because math can actually be applied to something. Biggest application? Fraud. Like accounting fraud and stuff like that. Our friend is happy though. For example, faked COVID-19 case counts. Someone, while during the quarantine, compiled all the first digit of coronavirus case data and compiled the results into a bar graph. Then we have the 2009 Iranian presidential election. Here's where there's possible voter fraud. Like this is for second digit, so the 0 is here. This is a little bit higher than it's supposed to be, and these last few digits are higher than they're supposed to be as well. 2020 presidential election, during the time people tried to keep linking fraud to everything. This was an interesting thing, where Benford's law seemed to fail Joe Biden's election data, while Trump's had natural distribution. Problem is, in precinct or county level, there is only small levels of magnitude, and this doesn't have to follow Newcomb-Benford's law. And then the Enron financial crisis, unfortunately, this was seen years after it happened. And as you can see, the 1 is like 10% more. So it's like 33% more chance that 1 is there than the, what is this? And then here's some other mentions that I couldn't find graphs for. Greece's Eurozone data that they used to apply to the Eurozone was regarded as highly improbable. And then federal courts accept this as evidence. So you could claim that it is improbable that results like this could have happened. And it's also been used to detect fraud in scientific papers relating coefficients. And the IRS and possibly the SEC also uses Newcomb-Benford's law to detect possible tax fraud, and the SEC stock fraud. Now the biggest downfall is Newcomb-Benford's law can never prove fraud, but it may suggest fraud. Now thank you. If you have any questions, you can email these emails. And here's all the sources. Here's the image sources. Now let's finish our example. Now the obvious thing to do is look into, there are websites like this online where you can plug in data and see if it works on Newcomb-Benford's law. As you can see, the first two companies have very eerily similar data. The second one doesn't even follow Newcomb-Benford's law, and this one follows Newcomb-Benford's law quite well. And now we're back on this. So now I guess he's going to put a complaint, and a year later, and that is it. So if you follow Benford's law, you're guaranteed getting $18 trillion on the stock market. Terms and conditions apply. You need to actually be a good investor. And thank you for watching.